Welcome back to another Forge College Explainer. All right, let's jump right in. Last time, in our lesson, Mapping EVM Mitigations to SVM Adaptations, we laid down the theory. Today, we're grabbing our orange and dark green ink pens, rolling up our sleeves, and sketching out the actual engineering blueprints for mitigations for attacks unique to SVM. You see, if building on Ethereum is like riding a train on safe and visible rails, building on Solana is a lot more like constructing a high-performance off-road vehicle entirely from scratch. It is incredibly powerful, but if you don't explicitly bolt the wheels on yourself, they are absolutely going to fall off. So here's our blueprint for today. We'll start with the EVM to SVM shift, then we'll tackle 3 major mechanical failures unique to Solana: missing signer checks, unsafe account ownership, and PDA misuse. After that, we'll head into QA testing, and finally, wrap up with your capstone security checklist.
Section 1. The EVM to SVM shift, from invisible rails to off-road assembly. This right here is the fundamental paradigm shift you have to make in your mental model. Over in the EVM, it's cozy. You have global variables like msg.sender. The network just inherently knows who is calling the contract and implicitly authenticates them. It's like having training wheels. But over in the SVM, Solana basically hands you a frat array of accounts. That's it. It's literally a bucket of loose parts. There's no implicit global context whatsoever. If you want to know who is calling your program, or if they're even allowed to be there, you have to write explicit runtime checks to verify every single piece of data.
Because of this explicit runtime environment, we see 3 primary attack scenarios that constantly catch Ethereum developers off guard. First up is the missing signer check, which happens when a program just assumes the caller is authenticated. The fix for that is an early is-signer guard. Second is unsafe account ownership, where a program naively trusts the data it's handed. The mitigation there is explicitly verifying the account owner. And third is PDA misuse, caused by bad derivation, which we fix with explicit seed checks. We're going to break down every single one of these right now.
Let's crack open that first scenario. Section 2. Missing signer checks. Did they actually sign this? What's really interesting here is this simple definition is signer. It's just a tiny Boolean property, true or false, living inside Solana's account info struct. But guys, this little Boolean is your absolute best friend. Because Solana doesn't have an implicit MSG sender. The presence of a cryptographic signature is a runtime property that you must actively observe. If you don't check this Boolean, well, a malicious user can just swap in someone else's public key, and your program will happily execute the transaction as if that other person authorized it. No way we're letting that happen.
So how do we actually bolt this wheel on? It takes 3 explicit steps. Step 1. When your program receives that flat array of accounts, you advance the iterator using next account info to grab the exact account you expect to be the authority. Step 2. Boom, you immediately write an if statement to check if not_signer.isSigner. You are literally asking the code, hey, did this account fail to provide a signature? Step 3. If they didn't sign, hit the brakes and return program error missing required signature. This explicit guard prevents anyone from sneaking an unauthenticated account into your off-road vehicle.
Moving right along to our second pitfall, Section 3, unsafe account ownership. Who really owns this data?
I love this. Identity theft is not a joke, Jim. It's a great reference. But seriously, this is a massive vulnerability. On Solana, anyone can pass literally any account into your program. If you just trust an account because it showed up in the array, it's the real-world equivalent of tossing your car keys to a random stranger just because they happen to be standing next to your car. You absolutely cannot trust the account data until you verify who actually owns and governs it.
Here's how we build out our defense against malicious cross-program invocations, or CPIs. Step 1. Grab that target account info from your iterator. Step 2. You explicitly verify that target.owner equals program ID. You're checking, right then and there, if the account is actually governed by your specific program. If an attacker tries to pass in a spoofed account that looks perfectly formatted but is actually owned by a different malicious program, this check catches it dead in its tracks. Step 3. Reject the transaction. Golden rule here, never ever operate on an account without verifying its owner first. Up next is our final major failure mode. Section 4. PDA derivation and misuse. Verify the seeds and the bump.
Program-derived addresses, or PDAs, are incredibly powerful for managing authority without private keys, but they introduce some serious ambiguity if you aren't careful. There are strict rules to follow here on our schematic.
First, never assume a past account is the correct PDA just because it looks like one. Second, always recompute the PDA seeds explicitly inside your program. Third, compare and verify the bump values to ensure it is the exact address you expect. And finally, reject any incorrect alternative PDAs. If you skip this, attackers can manipulate the seeds to spoof authority, basically hot-wiring your smart contract.
Now, knowing the fixes is only half the battle, right? Section 5, testing your mitigations. QA for your smart contracts.
In the engineering world, a mitigation doesn't truly exist unless a unit test actually proves it works. You have to intentionally try to break your own code. Here's the workflow for testing our first scenario, the missing signer check. Step 1. Construct a minimal, fake account info in your test environment and intentionally set isSigner to false. Step 2. Pass this unsigned account straight into your validation function. Step 3. Assert that the transaction fails, specifically looking for that missing required signature error. By writing these negative tests, you are mathematically proving that your guards are active and working. Which brings us to the final phase of today's workshop. Section 6, the security checklist. Preparing for the capstone audit.
To pass your capstone audit, you need to translate everything we just sketched out into a concrete, perfectly focused checklist entry. Every single item on your list needs exactly these 3 elements. First, the problem description. Clearly state the attack and the root cause, like missing signer check. Second, the mitigation code pointer. Show the exact defensive pattern you applied in your Rust code. And third, the verification step. Provide the specific test name or command the auditor can run to prove the mitigation works. 1 attack, 1 mitigation, 1 test. Keep it tight and keep it focused. So I'll leave you with this final, empowering question. Are your explicit runtime validations completely foolproof and ready for the capstone audit? If you've been following along and applying these explicit checks, verifying signers, checking account owners, validating PDAs, and writing the negative tests to back them all up, then the answer is a resounding yes. You are no longer relying on invisible rails. You've bolted the wheels on yourself. I highly encourage you to take this knowledge, head over to Forge College, and dive deeper into our Web3 resources and hands-on labs. This explainer was brought to you by Forge College. Keep building securely, stay curious, and I'll catch you next time.